Earth's core has stopped the 100-year countdown to disaster. The screen froze, then everything went black. 10 seconds later, the telescope woke up confused. Star trackers blind, counters spiking like hail on a tin roof. On the flight deck crossing the South Atlantic, a compass wandered, steadied, and the crew wrote it off as quirky ionosphere. It wasn't quirks, it was a dent. A soft spot in Earth's magnetic shield that lets charged particles dive lower than they should. Satellites cross it every day. Some tiptoe through, some don't. And here's the part that matters. The dent is drifting, splitting, and growing. If the engine below is changing, this is the first knock you hear upstairs. We start with the bruise you can actually see on a map, the South Atlantic Anomaly, the weak field corridor from Brazil to southern Africa, where satellites get slapped and astronauts see phantom shooting stars behind closed eyelids. That's the tell. Then we lift the floorboards. First, the dent in the sky. We'll show why the inner radiation belt sags low here, how Hubble schedules blackout windows, why CubeSats reset in clusters, and what NASA means when they say the dent has split into two lobes, creeping west and south. You'll meet the midnight patchers who turn instruments off on purpose and the ops teams who treat it like weather. Second, down into the engine room. The field isn't a neat bar magnet. It's made by a churning ocean of liquid iron alloy 2,900 kilometers down. We'll trace the Geodynamo, the convection, the helical flows, the Coriolis twists, and the deep mantle blankets that throttle heat. One of those blankets sits under Africa, and it's been a troublemaker for a long time. Third, the stethoscope through stone. Seismic repeats and waveforms that change just enough to say the inner core's rotation has been slowing and backtracking in recent decades. The debate is real. The signal isn't nothing. We'll keep the guardrails tight. Uncertainty isn't emptiness. Then, stakes. What weak, lumpy fields due to satellites, GPS timing, high-latitude flights, and power grids when the sun throws a punch? Not apocalypse, shrinking headroom. We'll walk through reversals and excursions in the rock record, Lachamp's 2,000-year stumble, and what survived, almost everything alive, versus what didn't exist then, our infrastructure. Finally, options, hardening parts, smarter forecasts, grid blockers, better maps of the core in motion. Will separate fear from budget. By the end, you'll know which headlines to ignore, which metrics to watch, and why the dent over the South Atlantic is the first line in a longer story that runs through molten metal. The dent in the sky, South Atlantic Anomaly, is the tell. Stretch a finger on a globe from southern Brazil to Namibia. That corridor is where low Earth orbit gets weird. The South Atlantic Anomaly isn't a hole. It's a place where the field at the surface is weaker, so the inner Van Allen belt, normally parked higher, slumps closer to orbiting metal and people. Protons that would mirror safely above 600 kilometers dive to 400. If your satellite lives there, you plan your breathing. Operators keep transit tables like airlines. Instrument off at 1312, back on at 1326. Hubble's UV detectors are blind on purpose through the SAA. Those black rectangles in image logs are deliberate. The International Space Station carries extra dosimeters. Crews report cosmic ray phosphenes, flecks of light the eye didn't earn. CubeSats are the canaries. With thinner shielding and cheaper memory, they cross the dent and wake up wrong or not at all. Error-correcting code saves most bit flips. Watchdog timers catch the rest, until they don't. Look at the fingerprint over time. ESA's swarm satellites mapped the weak zone as a deep blue basin decades ago. Now it's stretched and split. Two lobes drifting west and south by fractions of a degree per year. NASA updates call it a slowly splitting dent. Drift maps aren't drama. The ops teams treat them like tide charts. Add a solar storm and the waterline rises. The same orbit that was manageable on Tuesday turns red on Thursday. What's happening physically? Field lines control mirrors for trapped particles. Where the field is weak, mirror points dip lower. Inner belt protons ride those lines straight into orbits where they don't usually belong. The SAA is where Earth's magnetic dipole is offset relative to its center, and where non-dipole patches tug the geometry out of round. That geometry is downstream of the engine, but upstairs is where you see it first. Microstories carry the stakes. A gamma-ray telescope opens for an exposure, then a hair-early lobe edge peppers the detector with fake photons. A principal investigator sighs, recues the target, and extends the mask for tomorrow's pass by 90 seconds. In a ground room, an engineer watches a star tracker spit nonsense as proton hits sparkle like static. The flight computer hands off the gyros, holds attitude, and rides it out. Somewhere else, a tiny Earth imager loses a week of data to resets, clustered over longitudes west of Africa. The plot of timestamps looks like a skyline over the South Atlantic. It's not just orbit. High-altitude flights that skim the anomaly's northern fringe get dose upticks, well within occupational limits, but tracked. Dispatchers read space weather bulletins the way they read jet stream winds. HF radio sometimes goes scratchy. SATCOM takes the handoff. And yes, astronauts on the ISS spend more minutes per day in a hotter background during SAA transits. No one is cavalier, no one panics. The shape moves. In January 2021, the centroid sat near 26.6 degrees south, 49.1 degrees west, drifting roughly a third of a degree west per year. That sounds small. It isn't for an instrument whose safe window is minutes wide. A lobe splitting east means 2 blackout bites per orbit instead of 1 long nap. Mission planners tweak schedules like air traffic controllers routing around thunderstorms. It's the same storm every day in a slightly different place. This is where headlines go wrong. The SAA isn't proof the field is vanishing tomorrow. It's proof the field has texture that matters on human timescales. The anomaly has history. Ship logs and old observatories captured low intensity over southern Africa long before we flew swarm. What is new is the density of measurements and the speed of updates. We can watch the Dent breathe. And when the sun flares, the Dent helps it punch. A southward interplanetary field couples more easily into a weak, lumpy magnetosphere. Currents surge in the ionosphere. Radiation belts swell and dive. On a quiet day, the SAA costs you images. On a bad day, it tests your design. So why linger here? Because the Dent is a fingerprint from below. You don't get a sagging radiation belt without a sagging field. You don't get a sagging field here without a persistent patch of reverse flux at the core mantle boundary beneath southern Africa. Satellites taught us where to look. The next step is asking the engine why. Into the engine room, how the Geodynamo actually works. To make sense of a dent in the sky, we have to go where the field is born. Drop past crust and mantle to a spherical boundary 2,900 kilometers down. Rock gives way to metal. Above that boundary, the mantle, solid but slow flowing. Below it, a global ocean of liquid iron alloy, electrically conductive and always moving. At the very center sits the inner core, a solid iron-nickel sphere the size of the moon, growing grain by grain as Earth cools. The engine runs on heat and composition. Primordial heat from Earth's birth, radioactive decay, and latent heat released as the inner core crystallizes all drive buoyant motion. When the inner core freezes a little more iron onto itself, it rejects light elements, oxygen, silicon, sulfur, into the outer core. That compositional buoyancy is like adding bubbles to a pot. It enhances the simmer. Hot, light fluid rises, cool, heavy fluid sinks. Rotation twists those upwellings into columnar rolls aligned roughly with the spin axis. The Coriolis effect is the foreman here, organizing chaos into helical flow. Now add electricity. Moving conductive fluid cutting through a magnetic field induces currents. Those currents generate more field. If conditions are right, sufficient speed, conductivity, and size, the process becomes self-sustaining. That's the dynamo. Motion begets magnetism. Magnetism pushes back on motion, and the two settle into a restless balance. Inside the core, field strengths reach Millet-Slih levels. By the time that tangled field threads through the mantle and arrives at the surface, the largest scale piece looks like a dipole. But it's a dipole wearing a patchwork jacket. Two facts matter for the Dent we saw upstairs. First, the dynamo isn't free to do whatever it wants. The mantle regulates heat loss. The deep mantle isn't uniform. Seismic tomography reveals 2 continent-scale thermochemical provinces, the LLSVPs, under Africa and the Pacific, where shear waves slow. Think of them as thermal blankets with lumpy edges. Where the blanket is thick, less heat escapes the core. Convection underneath weakens. Where it thins, heat leaks faster, flow strengthens. That boundary forcing imprints itself on core motions. Second, the magnetic field at the core mantle boundary isn't smooth. Inversions of observatory and satellite data show concentrated patches where field lines point down or up strongly, and stubborn zones where the polarity is locally reversed relative to the main dipole. Under southern Africa, models consistently grow a reversed flux patch. That patch isn't a headline by itself, but it drags the dipole off-center and weakens the surface field in the South Atlantic sector. Stack enough years of evolution, and you get the sagging belt geometry that punishes satellites. Zoom in on the feedback. Rising, twisting columns win magnetic field lines, where shear is strong lines. Tangle and reconnect, converting magnetic energy back to heat and rearranging topology. Meanwhile, Lorentz forces, magnetic tension and pressure, push on the flow, altering the very motions that created the field. It's a living loop. Flow induces field, field resists and redirects flow. Small changes in heat flux or rotation can shift that balance and move energy between the global dipole and the smaller regional structures. We also see the engine twitch on human timescales. Geomagnetic jerks, abrupt changes in the secular variation, show up in observatory records every decade or so. They're signatures of flow reorganization, perhaps torsional oscillations, shear waves that ricochet through the outer core along cylinders aligned with Earth's axis. When such a wave reaches the core mantle boundary, the surface field's rate of change snaps to a different slope. That's not a reversal. It's a reminder that molten metal has its own weather. Inner core growth adds a slow beat. Evidence points to asymmetry, faster crystallization in one hemisphere than the other, which could nudge long-term patterns of convection. The inner core may also rotate at a slightly different rate than the mantle. Recent seismic analysis suggests that rotation has slowed and even backtracked relative to the surface in the past decade plus. Whatever the exact cycle, any change in inner core boundary conditions can tweak outer core flow and, indirectly, the field partitioning between dipole and patches. Numerical dynamos tie it all together. Give a model Earth-like rotation, conductivity, and buoyancy. Impose a realistic, heterogeneous heat flux at the core mantle boundary, and a self-sustaining field emerges. In many runs, a reversed flux patch forms beneath southern Africa and persists, drifting westward with the overall magnetic westward drift. As that patch waxes, the surface intensity over the South Atlantic dips, and the modeled inner belt sags lower. An SAA analog falls out naturally. In reversal-capable models, the growth and migration of such reverse patches often preface a global polarity switch. In non-reversing intervals, they still modulate regional weakness for centuries. None of this means the engine is failing. It means the engine is responsive. The mantle throttles the boil. The core reconfigures the field. The surface wears the consequences. When we say the SAA is a fingerprint from below, we're being literal. That low field is the integrated effect of heat, composition, rotation, and magnetism negotiating at depth. And if we want to forecast what happens to the Dent next, or how storms couple into a lumpy magnetosphere, we have to keep listening to the metal ocean the only way we can, by inverting the flicker of magnetometers and the whisper of waves that cross a planet. Hearing through stone, seismic clues the core is slowing. If we can't lower a thermometer into molten iron, we borrow earthquakes. When a big quake fires, it rings the planet with waves that bend, reflect, and refract through every layer. Some rays take a path we care about, PKE key, a compressional wave that dives through mantle, P, crosses the liquid outer core, K, pierces the solid inner core, I, then climbs out again. Compare that arrival to sister phases that skirt the inner core, and you get a clock. If the inner core rotates even slightly differently from the mantle, the structure it presents to the wavefront shifts, and arrival times drift by tenths of a second across years. The cleanest experiments reuse nature's metronomes, repeating earthquakes in the South Sandwich Islands. They rupture in nearly the same patch with nearly the same mechanism, producing waveforms that should match if the path is unchanged. Array stations at Yellowknife and Eielson have recorded these pairs for 3 decades. Stack the traces from 1991 against those from 2001, 201, 202, and you can watch small, persistent differences creep in, reverse, and creep back. It's like holding 2 vinyl pressings to the light and spotting a warp. For years, the dominant interpretation was steady super-rotation, the inner core rotating a hair faster than the mantle by about 15 degrees per year. Lately, the plot bent. Studies in 2023 to 2024, folding in new repeats through 2023, found the drift slowed around the late 200s, then changed sign. In plain speech, relative to the mantle, the inner core has been backtracking. That doesn't mean it spun the other way like a movie prop. It means the differential slipped through zero and went negative. Now the mantle is creeping ahead. Not everyone buys a single neat cycle. Some analyses argue the signal can be explained by changes in inner core anisotropy, how fast waves travel in different directions without requiring rotation changes. Others propose decadal oscillations, not a long march with the core mantle electromagnetic and gravitational coupling tugging the inner core into a bounded dance. What nobody sensible says is nothing changed. The waveforms changed. The task is to pin down which knob turned. Guardrails matter here. We're talking tenths of a second on phases that left the source thousands of kilometers away, traversed interfaces that scatter and ring, and landed on arrays inside noisy crust. That's why repeaters are gold. They cancel much of the mess. It's also why teams cross-check with other probes. Normal modes, free oscillations that hum after giant earthquakes, have hinted at similar rate differentials. Scattered waves off inner core structures and high-frequency coda that grazes its top show evolving textures. Threads point the same direction. Decadal change is real. What could slow and reverse the inner core's lead? Two levers. The magnetic handshake with the outer core and gravity's handshake with the mantle. Convection in the liquid iron drags field lines that thread the inner core boundary. That electromagnetic coupling can torque the solid sphere forward or hold it back as flow reorganizes. At the same time, dense patches in the lowermost mantle, especially around the African LLSVP rim, exert tiny but persistent gravitational torques that favor certain alignments. Nudge the flow, you nudge the torque. Nudge the torque, you change the differential. It's a coupled gearbox. Here's the part operators care about. Any change at that boundary can tweak the outer core's circulation. Not a switch flip, a bias. If the inner core's pace or orientation shifts, the pattern of shear in the fluid around it evolves, and that can alter where the dynamo stores magnetic energy. How much in the clean dipole, how much in regional patches like the one feeding the South Atlantic Anomaly. The seismic story doesn't predict the SAA's tomorrow. It explains why the Dent's next year isn't a guess pulled from thin air. You can see the science culture doing the work. One group publishes a slowdown, another remeasures with different arrays, a third adds Soviet and French nuclear test data from the 197s as fixed beacons. A fourth asks if doublets that should match but don't are telling us about topography on the inner core surface, not just spin. Vidal and colleagues call it backtracking, others call it oscillation. The disagreement is healthy and bounded by the same hard numbers. Meanwhile, there's a cross-check on surface clocks. If the inner core trades angular momentum with the mantle, tiny length of day variations, milliseconds on seasonal to decadal scales, should echo the exchange along with atmosphere and ocean effects. They do, though teasing apart contributors is a sport. Add that to geomagnetic jerks clustering near the same windows and a picture emerges. The core system breathes on human timescales. A small humor beat because the metaphor writes itself. Earth's engine light is blinking. The manual is in a language we're still learning to read. We're not pulling off the highway. We're checking the gauges, logging the miles, and listening for knocks that line up across instruments. Seismology isn't telling us doom. It's telling us motion. And motion in a machine that writes our magnetic weather. Tech hits first. The vulnerable stack in the next minute's 20 years. If the shield above us keeps getting lumpier, the first places you'll feel it aren't myth or biology. They're metal, code, and cable. Think in layers. Satellites live closest to the edge. In low Earth orbit, single event upsets, protons punching bits, show up as flipped memory, stuck pixels, and star trackers that suddenly see ghosts. Rad-tolerant parts and ECC memory scrub most flips before you notice. But scrubbing burns power and time, and deep dielectric charging isn't a bit problem. It's a miniature lightning problem. Electrons accumulate in insulation, discharge, and the arc can latch a power bus or quietly erode life. That's why high voltage detectors lower bias crossing the SAA, and why flight software carries SAA masks like a religious text. Navigation and timing hang on those birds. GNSS constellations are hardened, but their signals traverse an ionosphere that storms can wrinkle. Under a weaker, lumpier field, the same geomagnetic impulse can drive bigger irregularities. You'll see it as phase and group delay jumps, cycle slips, and a few more bad fixes that receivers must catch. Multi-constellation, multi-frequency gear rides through by switching bands and weighting measurements. Surveyors and grid phaser systems add local holdover and cross-checks. The playbook works, but the margin shrinks when space weather and a soft shield align. Imagery and science instruments already treat the Dent like terrain. Hubble has blackout windows, X-ray and gamma telescopes gate exposure. Earth imagers accept black rectangles in time series because cleaning peppered data is worse than a gap. For small sats, the economics bite. Consumer-grade parts plus SAA equals more resets, faster NAND wear, shorter missions. Teams compensate with watchdogs, configuration scrubbing, and clever autonomy. Safe the payload. Ride. Through resume. But every transition is thermal and mechanical stress. Over a decade, the anomaly's drift turns a comfortable timeline into tighter choreography. Now add the grid. When the sun throws a southward field CME, magnetospheric energy pours into the high-latitude ionosphere. Currents close through the ground and long conductors, pipelines, undersea cables, and especially power lines. Feel it as geomagnetically induced currents. Those JITs are DC offsets that push transformers towards saturation. Hot cores, distorted waveforms, tripped protection. Quebec in '89 was the postcard. A transformer hit its limit, a cascade followed in under 2 minutes. Today, utilities carry storm playbooks, series capacitors that block DC on critical corridors, neutral current monitors, thermal headroom, stage generation, reduced long-distance transfers. The difference in a weak field era is frequency and coupling. The same storm couples more efficiently where the field is low. That doesn't mean collapse, it means more long nights and more value in rehearsal. Aviation sits between. At cruise, cosmic radiation dose rises with altitude and latitude. Operators already track crew exposure and reroute polar flights during big events. The SAA is not the pole, but its weak field lets additional particles dip lower. Dose bumps that remain small compared with medical imaging yet still get logged. More immediate are radios and nav. HF can go noisy on disturbed ionospheres. Aircraft flip to SATCOM or procedural separation. Inertial and DME carry the load. The systems are built to degrade gracefully. The weak field trend just asks them to do it more often. Subsea and underground infrastructure aren't immune. Pipelines use cathodic protection, small DC currents to prevent corrosion. Storm-time jigs can overwhelm that bias through long metal runs, nudging corrosion in salty soils unless operators watch and adjust. Undersea fiber uses optical repeaters powered by DC. Sustained offsets can stress designs if not managed. Most networks survive because engineers are pessimists by trade. In a noisier magnetosphere, pessimism pays dividends. What changes in the next 2 decades is less what breaks and more what it costs to keep from breaking. For satellites, thicker shielding around sensitive nodes, rad-tolerant memories, higher scrub rates, autonomous SAA-aware mode changes, and constellation-level diversity, so a few resets don't dent the service. For timing and navigation, multiband receivers, ionospheric monitoring, local timekeeping, chip-scale atomic clocks, or disciplined oscillators that ride through brief GNSS stumbles. For grids, accelerate neutral blocking devices on long east-west lines, expand transformer thermal margins and replacements, add situational awareness via dense magnetometer and GIC sensors feeding real-time models that translate storm inbound into this substation this hour. Forecasting becomes a lifeline. More eyes on the sun, coronagraphs, L1 and L5 monitors, plus better CME orientation predictions narrow uncertainty on storm severity. On the home side, swarm-class successors and ground observatories keep the core field movie fresh, so SAA masks and hazard maps match where the lobes actually are. Think weather, not prophecy. Probabilistic, updated, good enough to plan. One more human moment. A flight director glances at a space weather alert and slides a polar departure south. A satellite ops lead widens an SAA mask by 90 seconds. A grid operator trims transfers across a corridor to keep a transformer cool. None of them save the world. They save Thursday. In a minus 20-year window, that's the job. Accept the dent, buy margin, and make the bad days ordinary. When the sun throws a punch, storms plus weak shield. Storms don't start at Earth. They begin on a star that forgets it's our neighbor. A coronal mass ejection lifts off. Billions of tons of magnetized plasma corkscrewing through space. Most miss. When one doesn't, timing and orientation decide the night. The critical detail is the interplanetary magnetic field it carries. If that field points south when it reaches us, opposite Earth's near-dayside field, magnetic reconnection snaps open the front door. Energy rushes in. You can watch the choreography in minutes. The dayside magnetosphere compresses. The nightside tail stretches thins, then reconnects explosively, slinging charged particles back toward Earth along field lines. Currents ignite in the ionosphere. Aurora's step equator ward, a beauty that's also a meter reading. Down on the ground, those time-varying currents induce voltages on anything long and conductive. Power lines, pipelines, undersea cables. In orbit, belts puff and dive, Electrons load up like storm clouds. Protons punch lower. Under a strong, clean dipole, coupling has to work harder. Under a weaker, lumpier field, like the South Atlantic sector today, it couples easier, deeper. The same storm that used to be a brisk night for operators becomes a shove. That doesn't mean collapse, it means headroom shrinks. And when headroom shrinks, margin is no longer a luxury, it's the plan. Operators read the storm in layers. Upstream, spacecraft at L1, SOHO, Discover, see the solar wind spike and measure the magnetic orientation. If it's southward, alerts go out. Minutes to an hour later, ground magnetometers start to arrive. Ionospheric models color in red blobs where conductivity and currents soar. That's when grids change posture. They reduce long-distance transfers, add local generation, watch transformer neutrals, and on lines with series capacitors, block the DC-like bias of geomagnetically induced currents. A hot core today is a failure in 6 months. Cooling it now is the win. In orbit, the playbook tightens. Satellites widen SAA masks and raise thresholds to avoid deep dielectric charging. High voltage detectors lower bias across broader longitude bands. Telemetry slows. Not because space is romantic, because downlinking during a surge risks saturating receivers. Constellations lean on redundancy. A few birds can reset without taking a service dark. Star trackers hand off to gyros more often. Operators accept degraded pointing rather than cooked pixels. Pilots get storm briefs like weather. On polar routes, HF radio may fade. They move to SATCOM or accept procedural separation. Dispatchers slide tracks equator-ward when alerts stack up. More time, more fuel, less dose, and fewer comm headaches. Flight management systems are happy with inertial and DME if GNSS falls out for minutes. Crews already log radiation dose. Storm days just bump the totals a hair. For pregnant crew, scheduling changes. For passengers, the flight feels like every other long night over water. Pipelines and cables hum quieter and worry more. Cathodic protection systems watch their set points. During storms, GICs can undo that protective bias and accelerate corrosion in salty soils unless controllers nudge it back. Undersea repeaters ride DC feeds. Network engineers monitor for offsets and temperature climbs, prepared to rebalance loads to keep electronics comfortable. None of this is new. The weak field overlay just raises the frequency of drill nights. Here's the translation that matters. Identical storm, worse outcome, and a softer, lumpier shield. Quebec 89 under today's SAA geometry wouldn't guarantee a blackout, but more grids would feel it, and more transformers would flirt with saturation. Halloween 2003's electron storms would feed deeper, and more satellites would pick up latent charging scars that turn into failures months later. The risk isn't cinematic, it's cumulative. Forecasting buys time. Better chronographs sharpen CME speed. L1 and a future L5 Sentinel nail arrival windows and orientation. Assimilative models stitch solar wind to magnetosphere to ground, turning watch for hours into this station, this hour. Utilities run storm response drills with those maps, not just K-index headlines. Satellite teams fold real-time geomagnetic maps into autonomy, expand SAA masks for the next orbits, then shrink them as the tail relaxes. Aviation ties space weather advisories to route planning software as cleanly as winds aloft. A weak field doesn't doom. It demands rehearsal. The dent we saw over the South Atlantic is a local fragility at global scale when the sun cares to test it. So the culture shifts. Engineers budget for storm days the way cities budget for snow. Series capacitors on vulnerable corridors. Neutral blocking devices where they buy the most margin. Transformer replacements with fatter cores. Multi-band GNSS receivers with better ionospheric estimation. Rad-tolerant parts as defaults, not luxuries on. Spacecraft that must live in low orbit. Meanwhile, the checklist gets more ordinary. A satellite ops lead slides a mask 90 seconds wider and saves a detector. A grid operator trims a transfer and keeps a transformer cool. A dispatcher bends a track. A space weather forecaster sees a southward flip and hits send. Multiply that by 100 small rooms on a storm night, and the punch lands, but it doesn't break anything that wasn't already cracked. That's the point to carry forward. The sun throws punches, the shield is softer in places, the shield is softer in places. The story isn't apocalypse, it's headroom, and headroom is something we can buy. People under strained skies, medium-term exposure, 20 to 100 years. Pull the camera down from the storm maps and into cabins, clinics, and cockpits. Over the next few decades, the sky doesn't turn hostile, it gets noisier. The baseline dose at altitude ticks up modestly as the weak field sectors let more particles skim lower. Airlines already track cumulative exposure for crews. That continues, tighter rostering on polar and high-latitude legs, more attention to pregnant crew, more use of real-time dose forecasts layered with space weather advisories. For most travelers, the extra dose on a long haul remains small compared with medical imaging. The line is honest. Your CT scan still beats your flight, but the ledger grows more carefully. Satellites are the eyes we use to watch the climate, and the Dent steals minutes from those eyes. Small gaps don't look like drama. They look like missing tiles in time series mosaics. That's fine when you're mapping clouds. It's harder when you're tracking sea ice edge, wildfire aerosol, or short-lived methane plumes. Agencies build redundancy, 2 instruments instead of 1, cross-calibration between constellations, smarter gap-filling models, but the cost shows up in calibration campaigns and longer error bars. Meanwhile, the ionosphere's noise floor rises during weak field storm seasons. HF links and GNSS signals wander more. The weather models that assimilate satellite radiances work harder to flag corrupted data. Not broken, busier. There's a chemistry footnote worth caution, not panic. High-energy particles catalyze odd nitrogen and odd hydrogen that can tweak ozone, especially in polar regions during big solar proton events. A weaker, lumpier shield can let a few more of those events reach the upper atmosphere. Models say the effects are patchy and brief. They matter for a subset of radiation budget calculations and satellite drag forecasts. They don't rewrite the climate story. That belongs to greenhouse gases and heat in the ocean. Wildlife lives closer to the field than we do. Birds, sea turtles, salmon, and even some insects rely on magnetic cues stitched together with stars, smells, and landmarks. A noisier map forces a reweighting. You'll see more errant hatchlings on certain beaches in SAA-adjacent years, a few more migrating birds that favor celestial and olfactory cues when geomagnetic storms rattle the compass. The species with flexible playbooks adjust. The specialists struggle on the margins. Conservation biologists add magnetic weather to nest timing and routing studies the way they added light pollution and wind farms. Another variable, not a verdict. Navigation on the ground keeps a paper atlas behind a GPS. Surveyors already run multi-band, multi-constellation receivers with local base stations. They'll lean more on inertial backups and terrestrial beacons when the ionosphere hisses. Ports and precision agriculture do the same. It's an organizational shift. Treat position like weather, with alerts and playdowns rather than like a constant. The hidden benefit is resilience. The drills you write for magnetic noise help when jamming and spoofing show up for other reasons. The human signal sits in clinics and policy. Radiation protection bodies update crew dose models with weak field terms. Regulators tighten reporting and provide clearer guidance for at-risk pregnancies. None of this feeds headlines. Airlines invest in cabin dosimetry that logs cumulative exposure per aircraft. Unions negotiate smarter scheduling. It feeds trust. On the ground, utilities keep a second set of tools at the ready. Neutral current sensors become standard on long corridors. Transformer replacements favor higher thermal headroom and lower core loss. Pipeline operators couple space weather alerts to cathodic protection control rooms, nudge bias during storm hours, then return to set points. Undersea cable consortia share JIC-IC data to coordinate repeater loads. The change over 20 to 100 years is cultural. Space weather stops being niche. Will we see more auroras at low latitudes? Sometimes. During strong cycles, the oval wanders equator-ward, and more people get a free light show. That's a joy with a spreadsheet attached. Those same nights are busier for operators. It's a pattern, not an omen. A humor beat to keep the scale honest. The most dangerous radiation in.
Your year is still in a hospital, not at 35,000 feet. The Dent turns rare bad days into costlier ones, and ordinary days into ones that need a checklist. There's a quiet frontier in data stewardship. If the Dent trims minutes from critical sensors, you replace exposure with statistics. That means archiving raw data, publishing uncertainty, and funding overlaps. Old satellite up, new satellite up, run together, then retire the elder. It sounds boring. It's how climate baselines survive noisy skies. In classrooms, the map of Earth's field stops being a static poster. Kids learn that the poles wander, that the South Atlantic is a known weird zone, and that pilots, linemen, satellite ops, and park rangers all read the same auroral forecast for different reasons. A shared language reduces rumor. Final stakes for this window are modest and human. Fewer surprises at altitude, slightly more expensive space science. Wildlife researchers adding one more column to their spreadsheets. utilities with better drills. The sky is stranger, not cruel. Our job is to make it legible. Reversals and excursions, the messy middle, not doomsday. To understand where a dent might lead, we need the long record of when the field stumbled before. Rocks carry receipts. Fresh lava cools, iron minerals freeze like tiny compass needles, and sediments align grains as they settle. Stack enough of those records across the world and a pattern emerges. The field doesn't march smoothly. It lurches, weakens, gets multipolar, then reforms. Sometimes the poles trade places. More often they flirt and snap back. The big word for a full trade is reversal. Those are rare on human scales and slow on their own clock, taking hundreds to a few thousand years. The smaller, more common stumbles are excursions. Think of them as near flips. The dipole weakens to a small fraction of its usual strength. The magnetic poles wander far from the geographic poles, and the map turns messy with several strong lobes at odd latitudes. Then the original polarity reasserts itself. The best-known example is the Lost Champ excursion about 41,000 years ago. For a couple millennia around that window, the dipole sagged to roughly 10% of today's value, and the virtual poles zipped around. Auroral ovals wandered toward lower latitudes in models that connect core, magnetosphere, and ionosphere. Tree rings and ice cores picked up spikes in cosmogenic isotopes, beryllium, tin, and radiocarbon, because more cosmic rays reached the upper atmosphere when the shield thinned. That's a clean signature of a leaky field. It isn't a mass extinction signature. Humans lived through it, hunted, painted caves, crossed water. Life's big systems, the atmosphere, the ocean, the crust, did most of the protecting. What does a stumble feel like from the surface? Not a single day of spinning compasses. Instead, generations of incremental oddness that instruments notice more than people. At high latitudes, compasses wander off their tidy tracks more often. At mid-latitudes, they stay useful, just noisier. During storms, auroras appear farther from the poles. Aviation dose ticks up on certain routes. Operators adjust. Satellites take more hits. We plan around them. The sky gets stranger. The ground keeps its habits. Under the hood, excursions look like the growth of reverse-flux patches at the core mantle boundary. In many numerical dynamos, when those patches expand and link up, the global dipole loses dominance. Several regional poles pop up, and the surface field becomes a quilt of lobes that migrate and morph. If the reverse patches connect deeply enough, the system tumbles into a new dipole with opposite polarity, a full reversal. If coupling changes, flows reorganize, or boundary forcing eases first, the multipolar state collapses back into the original polarity, an excursion. The choreography is similar either way. The outcome hinges on thresholds. Timelines matter because they buy adaptation. Even fast excursions unfold over centuries. That gives hardware designers, grid planners, and pilots cycles to adjust. It also demolishes the myth of a cliff. There's no switch that turns the field off. Even at lows, shielding persists. It's weaker and lumpier, which is exactly the world we've been describing. More coupling during storms, more careful operations, few surprises for biology at the surface. The South Atlantic's role in this isn't prophecy, it's pattern. The African sector shows up in paleomagnetic archives as a magnetically odd neighborhood repeatedly. Hearths in southern Africa from a few thousand years ago capture unusually low intensities. Coastal lavas on both sides of the South Atlantic record direction changes that don't align with a simple dipole drift. In models and in inversions, a reverse flux patch beneath southern Africa is a habitual troublemaker. Sometimes it seeds the messy middle. Sometimes it just keeps the SAA alive. Debunk a pair of headlines while we're here. A reversal does
Not erase the atmosphere. Solar wind stripping is a problem for unmagnetized planets over millions of years, not for Earth during a 1,000-year reconfiguration under an atmosphere as thick as ours. And no, a flip won't fry the surface with radiation. It will raise upper atmosphere ionization during storms and complicate space operations. That's budget and training, not doomsday. So, if the messy middle arrived in our century, what would change? Satellites would update SAA-style masks to follow multiple shifting dents. GNSS receivers would lean harder on multi-band corrections and local augmentation. Grids would treat severe geomagnetic storms as more frequent stress tests and expand DC blocking and thermal headroom. Aviation would routinize space weather the way it routinizes volcanic ash. Wildlife research would add magnetic noise to a list already topped by habitat loss. The meaning is plain.
Reversals and excursions aren't cliff edges. They're long, navigable valleys. Technology feels them first. People feel them as inconvenience, cost, and sometimes unexpected auroras over cities that don't usually get them. The right response isn't fear, it's rehearsal. Africa's deep shadow LLSVPs and the flux patch. Meanwhile, beneath the place where the dent bites hardest, the mantle hides a continent-sized culprit. Seismologists call it an LLSVP, the African Large Low Shear Velocity Province. In plain terms, it's a vast domain at the base of the mantle, where seismic waves slow, meaning the rock there is hotter, different, or both. It rises 1,000 kilometers above the core, mantle boundary, spreads for thousands more, and its edges aren't neat. They're steep, crenulated, and loud in the data. Exactly the kind of boundary that would steer the engine below. Why does a slow mantle patch matter to a magnetic field? Because the core's heat escapes through the mantle, and that escape isn't uniform. An LLSVP is a thermal blanket with a frayed hem. Where it's thick, it insulates, throttling local heat loss and damping convection in the liquid iron beneath. Around its rim, where the blanket thins or tilts, heat leaks faster, speeding flows. That contrast sets up shear, fast columns sliding past slower ones. And shear is where magnetic field lines get bent, braided, and sometimes flipped. Numerical dynamos that feed in an African-style heat map tend to grow a persistent reversed flux patch under southern Africa, not once, often. Maps built by inverting observatory and satellite data see the surface consequences of that patch. At the core mantle boundary, the radial field shows a stubborn island where polarity is opposite the main dipole. That island migrates westward with the planet's magnetic westward drift, waxes and wanes with decadal flow changes, and crucially projects a weak zone to the surface over the South Atlantic. It's a clean chain. LLSVP edges modulate heat. Heat patterns modulate core flow. Flow shapes the reversed flux patch. The patch drags the dipole off-center and thins the field above Brazil, Namibia. The dent in the sky is the headline. The byline runs through Africa's deep shadow. This isn't hand-waving. Seismic tomography from multiple teams pins the LLSVP's footprint beneath Africa and outlines a dome that may reach higher beneath eastern Africa, consistent with hotspots and rifting topside. Along its southwestern and northwestern flanks, detailed studies find sharp transitions in shear velocity. Walls, not gradients. In the same sectors, geomagnetic models favor strong boundary forcing, places where core flow likely shears and curls. Add archaeomagnetic receipts, Iron Age hearths in southern Africa with unusually low intensities 2 to 3 millennia ago. Coastal lavas on both sides of the South Atlantic recording directions that defy a simple dipole wander. Different archives, same neighborhood acting strange. The chemistry debate rides alongside the thermal story. Are LLSVPs just hotter mantle, or do they carry dense, compositionally distinct material, recycled oceanic crust and primordial reservoirs, piled at the base for hundreds of millions of years? Seismic discontinuities inside the African dome and its sharp edges suggest thermochemical character. Hotter and a bit heavier, stable enough to persist, lumpy enough to shape flow. If it's long-lived, so is its magnetic influence. That would explain why the African flux patch keeps reappearing in models, and why the South Atlantic sector shows repeated weak field episodes in the paleo record. Watch how this plays out in simulations that can reverse. When you impose heterogeneous heat flux shaped like Africa's LLSVP, reversed flux patches blossom beneath southern Africa and the Pacific counterpart. If the African patch grows large and links with neighbors, the global dipole sags, multiple poles sprout, and the system leans toward a reversal. If coupling shifts, say a change in outer core shear due to torsional oscillations, or if boundary forcing
relaxes, the system snaps back, an excursion instead of a flip. Either way, Africa's deep shadow is the staging ground. On human timescales, the manifestation is practical. As the reverse patch strengthens or drifts, the surface weak zone over the South Atlantic broadens, splits, and slides. That's exactly what swarm era maps show. The SAA lengthening, budding an eastern lobe, its centroid creeping west-southwest by fractions of a degree per year. Mission planners don't need to peer through the mantle. They need tomorrow's lobe outline. But knowing there's a deep driver explains why the dent won't behave like a random scar. It's being fed. The frontier now is fusion of datasets. Geodesists and seismologists refine the LLSVP's rim. Geomagnetists assimilate swarm and observatory records to update core surface flows. Modelers nudge heat maps and watch reverse patches evolve. When those three agree, rim here, flow shear there, flux patch growing, you trust the next year forecast a little more. not dates for flips. Decadal guidance for dents. So the story under Southern Africa isn't doom, it's persistence. A deep mantle giant throttles the boil. The core responds with a local flip of polarity. Satellites feel it as a dent that won't sit still. Africa's deep shadow keeps writing on the sky. The smart move is to keep reading, watching the core in real time, forecasting in jerks. We don't guess where the dent will drift. We measure, subtract, and update. Start with our eyes in orbit. ESA's Swarm constellation, 3 identical satellites at staggered altitudes and local times, samples the field with vector magnetometers precise enough to feel a subway train under a city. Their trick isn't just sensitivity, it's geometry. Different orbits let scientists peel off external currents in the ionosphere and magnetosphere, leaving the slower, deeper baseline that belongs to the core. On the ground, observatories do the slow work of patience. Hermanus, Kakioka, Chambon-La-Forêt, Honolulu, stations that have recorded direction and intensity every day for decades. Their curves show secular variation, the steady lean of lines westward, and then, suddenly, snaps. Those snaps have a name: geomagnetic jerks. They're not storms, they're changes in the rate of change, kinks in the secular trend that sweep the globe over months to a couple of years. Modelers see them as postcards from the core. A torsional wave reached the boundary, the flow reorganized, the surface field slope shifted. Turn those mixed signals into a movie, and you need data assimilation, the Geodynamo's version of weather forecasting. Start with a physics-based core model that respects rotation, buoyancy, and Lorentz forces. Feed it swarm and ground data with their error bars. Let the model's equations pull the field forward in time while observations tug it back toward reality. The output isn't prophecy. It's an evolving best estimate, with uncertainties that shrink where the data are dense and widen where they aren't. Like over the oceans, unless you float an ocean-bottom magnetometer and buy yourself leverage. That assimilation delivers 2 things operators can use. First, core surface flow inversions. Maps of where liquid iron is likely shearing faster or slower today. Those flows steer reverse flux patches, including the African one feeding the SAA. Second, decadal forecast of the main field. Not next week weather, but SAA lobe here, not there, a couple of years out. Enough to widen an instrument mask in 2027 now, not after your detector takes a peppering. Jerks slot into that pipeline as regime change markers. When observatories light up with the same kink, assimilation schemes admit a new flow pattern. Forecast downstream shift. You don't announce a reversal, you nudge a lobe outline, bump a drift rate, and push that change into the files mission planners actually load. Weather, but for molten metal. Meanwhile, external space sensors keep you from blaming the core for a storm. L1 monitors, SOHO, DS cover, watch the solar wind and its magnetic orientation. Ground magnetometers map the instant response. Subtract that fast wiggle, and what's left is the slow hum. That subtraction is why swarms, local time sampling matters. You can separate noon-side ionospheric loops from midnight-side tail surges and from the deep signal you care about. Do it poorly, and you'll discover a core jerk every time the sun coughs. The frontier is coverage. A swarm follow-on that drifts in local time would untangle day-night biases better. More ground stations in the Southern Ocean and Africa would pin the SAA's edges tighter. Ocean bottom magnetometers, hard, expensive, worth it, would cut the blue deserts on model maps down to oases. Each new sensor shortens error bars. Shorter error bars mean fewer surprises. There's a shop floor deliverable at the end of this alphabet soup. Satellite teams want near-term hazard maps, where the SAA lobes will be this quarter, with confidence intervals.
Grid operators want decadal guidance. Is westward drift accelerating enough to change regional coupling under strong storms? Airlines want simple flags. DOS and comms risk baked into route tools. The science can do that without overselling. Publish updates on a schedule, note the uncertainties, show last year's forecast versus what really happened, and trust will follow. A human beat to close. Somewhere, a coder pushes a new SAA polygon to a spacecraft the same day a geomagnetic jerk rolls through observatory logs. In a lab, a modeler reruns an assimilation with that jerk admitted. The African flux patch shifts a hair. The 18-month forecast lobe nudges south. None of it is dramatic. All of it is the difference between guessing and steering. Weather, but for molten metal. Can we patch a planet? Options, trade-offs, reality. Let's level with the question everyone asks at this point. Can we fix the shield? Not fix like swapping a transformer. Fix like shaping a planetary force field that's born 2,900 kilometers below us and braided through space by the sun. The honest answer is yes, in narrow ways, no in the grand way, and the middle is where we should spend money. Start with what works now. Hardening. Spacecraft survive by assuming space is a vandal. Rad-tolerant memories with error-correcting codes, configuration scrubbing to rewrite flip bits, triple modular redundancy where a vote beats a glitch, and thicker shielding around the parts that can't blink, clocks, power buses, star trackers. High voltage detectors lower bias in hot zones. Software carries SAA polygons and switches modes automatically. You don't make the dent go away, you make it boring. On the ground, grids by margin the old-fashioned way. Physics. Series capacitors block the DC-like geomagnetically induced currents on long corridors. Neutral blocking devices choke jigs at substations. Transformer replacements grow heavier cores with thermal headroom, so a storm night is heat, not failure. Dense magnetometer and GIC sensors feed real-time models that translate an upstream alert into this station, this hour. Pipelines couple space weather bulletins to cathodic protection controls and nudge bias through storm windows. Fiber consortia watch repeater power and rebalance when DC offsets creep. None of this is sci-fi, it's procurement. Procedures scale what hardware can't. Airlines treat space weather like ash and turbulence. Reroute polar flights under advisories, adjust altitudes to trim dose, and brief crews for HF fades and GNSS stutters. Satellite operators widen masks, lower detector voltages, and slow non-essential activity through storms. Utilities stage generation, reduce long-haul transfers, and staff overnight with people who've drilled. In every sector, drills make the bad night look like a long day. Forecasting is the multiplier. More eyes on the sun, a sentinel at L1 and another at L5, shrink the uncertainty on CME arrival and magnetic orientation. Better data assimilation stitches solar wind to magnetosphere to the ground, turning a K-index headline into a substation-level forecast. On the deep side, swarm-class successors and more observatories keep the core field movie current, so SAA masks match where the lobes actually go. Think weather services, not oracles. Probabilistic, updated, verified. Now for the tempting stuff. Artificial magnetospheres. In space, they work at small scales. Plasma tethers and mini magnetospheres can wrap a spacecraft in a comet-sized bubble, bending the solar wind around it with modest power. Scale that to a city, and the numbers go feral. Field strength falls with the cube of distance. To push radiation back tens of kilometers, you need currents and coils that make a fusion plant blush. Failure modes are ugly. A storm that overdrives the system turns protection into a source of induction you didn't budget for. As a lab, it's fascinating. As municipal engineering, it's fantasy. Geoengineering the field globally sits farther past the line. Proposals surface, planet girdling coils, lunar orbit dipoles, orbital current loops to add or bias Earth's field. The energy cost is immense, the control is fragile, and the outcome is uncertain because you're not just adding a field, you're changing how the solar wind couples to a magnetosphere that's already asymmetric. You can make a weak region worse. Worse, you create a single point failure, a human scale device that entire hemispheres depend on. That's a bet against entropy and politics at the same time. So where's the best return? Harden what must work, forecast, like you mean it, retrofit the grid, and write standards that make resilience a default. Multi-band, multi-constellation GNSS receivers with local augmentation and good holdover clocks. Default rad tolerance for LEO spacecraft that do anything critical. GIC blockers on vulnerable east-west lines first. Transformer specs that assume storm nights and weak field decades. Aviation tools that integrate dose and comms risk into the same screen as winds aloft. And fund the sensors, swarm follow-ons, ground observatories, ocean bottom magnetometers, and upstream solar sentinels, because you can't steer if you don't see. There's a softer patch we can make too. Shared playbooks. Utilities, airlines, satellite ops, and space weather centers running joint exercises, speaking the same alert language and publishing after-action reports. The Dent makes successes invisible. The work prevents the story. That's the point. You patch a planet by lowering surprise. Could the core be nudged? Not by us. Seismic and magnetic couplings are the core's domain. Heat, buoyancy, rotation, and the mantle's deep blankets call the tune. Our lever arm lives above the crust. Spin there. The shield isn't. Failing. It's messy, Our job isn't to move molten metal, it's to keep people and machines comfortable while it breathes. Scenarios: 4 paths and their price tags. Think in paths, not prophecies. The Dent we've been living with can evolve 4 ways within a century-scale window. Each is survivable. Each has a bill. First path: stabilization. The dipole slide slows, core flow reorganizes, and the South Atlantic lobe stops stretching. Not a snapback, just a plateau. Price tag: maintenance mode. Satellite ops keep SAA masks current, but don't chase accelerating drift. Constellations budget modestly higher, rad-hard parts as defaults, not extremes. Grids continue installing series capacitors on the longest east-west corridors and replace end-of-life transformers with fatter cores baked into ordinary procurement. Space weather forecasting expands with an L5 Sentinel and a Swarm follow-on, paid once, amortized across sectors. Aviation folds DOS tools into route planners, then moves on. This path costs billions, spread thinly and quietly prevents headlines. Second path: continued weakening. The dipole keeps leaking energy into regional structure. The SAA grows, splits, drifts faster. Satellites lose more minutes to masks. Small sats retire earlier unless designs upgrade. Price tag: higher capex per kilogram in low Earth orbit. Hardened memories, configuration scrubbing by default, shielded clocks, and autonomous SAA-aware modes become table stakes. Ground: utilities accelerate neutral blocking devices on vulnerable corridors and roll out dense GIC sensors to turn alerts into substation guidance. Aviation adds more polar detours in storm seasons and tighter crew rostering. Forecasting must sharpen. Coronagraphs, upstream monitors, and assimilative models that deliver sub-regional risk. Expect recurring operational surcharges and midlife retrofits, not a single big program. Third path: excursion. The system dips hard into a multipolar map for centuries and snaps back without a flip. That's Lashamp, like dipole reduced to a small fraction, several strong lobes wandering. Satellites treat a handful of dents, not one, and those dents migrate year to year. Price tag: constellations built for churn. Redundant orbits to maintain service when regional masks bite. Payloads with higher voltage margin. Star trackers that fail over the gyros gracefully. Ground autonomy that digests weekly hazard maps. Grids expand DC blocking programs from corridor patching to backbone standard, with thermal headroom mandated in transformer replacements. Regulators write space weather compliance into grid codes the way wildfire rules entered Western power law. Aviation routinizes space weather. Dose and comms risk on the same pane as winds and convective signets. More frequent latitude bends, more fuel in the plan. Forecasting becomes an operational utility. Verification builds trust. The cost is steady and cultural. Drills, spares, and smarter defaults. Fourth path: full reversal on a long clock that our great-grandchildren may still be inside. The messy middle looks like the excursion path extended. Multiple lobes, rapid virtual pole motion, dipole rebuild inverted. Price tag: the same tools, scaled and kept funded for longer. No new physics. More patience. Procurement cycles assume abnormal is normal. Critical space services move toward mixed orbits. LEO for latency, MEO-GEO for resilience. So regional dents don't blind everything at once. Navigation leans into multi-band, multi-constellation, local augmentation, and high-quality holdover clocks across critical timing applications. Utilities complete DC blocking on long lines, and transformer spares move from hope to inventory. The money is real, spread over decades, and cheaper than learning on blackout nights. Across all paths, we need checkpoints, metrics that tell policymakers when to shift from maintenance to acceleration. Watch the global dipole moment. If the century-scale decline steepens beyond historical bounds, move from Path 2 budgets to Path 3. Track the SAA's drift and lobe count. A persistent second or third lobe with rising drift rate is a trigger for constellation-wide mask and shielding upgrades, not piecemeal patches. Log geomagnetic jerks and how forecasts degrade afterward. Repeated underperformance means funding the next swarm and ground gaps now, not after a mission suffers. On the sun-facing side, invest when L1, L5 accuracy reduces false alarms and misses. Utilities buy fewer sleepless nights per dollar when alerts are specific. Set policy triggers in plain language. If neutral currents exceed thresholds at N substations during 2G4 storms in a cycle, mandate DC blocking on named corridors. If satellite anomaly rates per transit through SAA double over 5 years, set a rad-hard baseline for government-funded LEO missions. If GNSS cycle slips correlate with weak field storms above a published rate, require multi-band receivers and certified holdover on.
Critical infrastructure. These aren't panic switches, they're budget valves. There's a fifth, quiet path: ignorance. Delay the sensors, skip the drills, fly consumer parts through a noisier sky, and act surprised. That path is cheap on Tuesday, expensive on Thursday. Choose one of the first four, fund the eyes and the boring gear, and the Dent becomes logistics. The price tag isn't fear, it's foresight. Myths versus reality. What to stop saying, what to start doing. Let's clear the air. Myth 1. The field is collapsing and life is in danger. Reality. The dipole is weakening modestly on century scales, while regional structure, especially over the South Atlantic, has grown louder. Even during deep lows like Lasham, shielding persisted. The risks are technological and operational, not existential. Treat it as weather that affects infrastructure, not a sky that falls. Myth 2. The South Atlantic Anomaly means a flip is imminent. Reality. The SAA is a regional weak zone tied to a persistent reversed flux patch beneath southern Africa, modulated by the African LLSVP. It can intensify, split, and drift without triggering a global reversal. It's a fingerprint of deep dynamics, not a countdown clock. Myth 3. A reversal turns off the field and the atmosphere peels away. Reality. Reversals and excursions are multipolar phases with weaker, lumpier shielding that unfold over centuries to millennia. The atmosphere and residual field blunt radiation. The consequences are more coupling during storms, more ops costs, more drills, not surface catastrophe. Myth 4. Compasses will spin wildly overnight. Reality. High latitude compasses meander as poles wander. Mid-latitudes remain usable with correction. The change is gradual. Instruments notice first. People notice paperwork. Myth 5. We can fix the core with giant coils. Reality. We can't steer convection 2,900 kilometers down. Planet-scale artificial magnetospheres are energetically and operationally implausible, with nasty failure modes. The leverage we do have lies in hardening, forecasting, and standards. So what do we stop saying? Stop framing every SAA update as doom. Stop treating pole motion as a siren. Stop implying that storms plus a weak field equal blackout destiny. Hype erodes the trust we need when we issue real advisories. What do we start doing? 3 buckets. See better. Build tougher. Practice together. See better. Fund a swarm-class successor and keep ground observatories healthy, especially in the southern hemisphere. Add ocean-bottom magnetometers to shrink blind spots. Put a solar sentinel at L5 to complement L1, and invest in assimilative models that translate upstream CME data into sub-regional risk on the ground. Publish decadal core field forecasts with uncertainties and verify them publicly, so operators can plan masks, routes, and maintenance windows. Build tougher. In LEO, make rad-tolerant memory, configuration scrubbing, and autonomous SAA-aware modes defaults. Shield clocks, power buses, and star trackers. In GNSS-dependent sectors, deploy multi-band, multi-constellation receivers with ionospheric estimation and certified holdover clocks. In grids, prioritize series capacitors and neutral blocking devices on long east-west corridors. Specify higher thermal headroom for replacement transformers. Expand dense GIC and magnetometer networks to turn alerts into targeted actions. For pipelines and cables, integrate space weather inputs into cathodic protection and repeater power management. Practice together. Treat magnetic weather like aviation treats turbulence. Share data, standard advisories, and drills. Utilities, airlines, satellite ops, and space weather centers should run joint exercises, agree on alert thresholds, and publish after-action reports. Write clear policy triggers. If neutral currents exceed set limits at named substations during 2 G4 storms in a cycle, mandate DC blocking on those corridors. If SAA-related satellite anomaly rates double in 5 years, raise rad-hard baselines for public missions. Get the incentives right. Tie insurance rates and procurement standards to resilience metrics. GIC mitigation in place, multi-band timing receivers certified, radiation hardening levels documented. Require overlap in critical satellite missions, so calibration survives noisy skies. Archive raw data and uncertainties to keep climate baselines intact when gaps widen, and communicate like adults. Separate the core's slow choreography from the sun's fast punches. When a geomagnetic jerk rolls through observatories, explain what it means for next year's SAA lobe not for civilization. When a southward field CME is inbound, name the corridors and hours, not just the K-index. Quiet credibility buys compliance on long nights. The through line is simple. Myths promise drama. Reality demands maintenance. We don't need miracles. We need eyes, margin, and muscle memory. So a dent in the sky stays a line item, not a legend. The human.
Contract. Maintenance, memory, and meaning. If there's a contract here, it isn't with a planet that promises calm. It's with each other. About how we keep things working when the shield gets noisy and the map keeps changing. Maintenance first. Systems last when we build for repair. Satellites with swappable software and graceful safe modes. Grids with spare transformers on a shelf, not a brochure. Airports where a space weather line sits beside winds aloft and a reroute is routine, not heroic. Redundancy sounds expensive until you price a prize. Duplicate sensors on a spacecraft so one can nap through a storm. 2 timing sources in a substation plus a holdover clock, so a brief GNSS stumble doesn't ripple into a city. Parallel supply on a cable landing station so a DC offset doesn't cook a repeater while a technician is driving in. Boring buys time. Time buys choices. Memory is next. The Dent steals minutes from eyes that record climate, oceans, and air. If we want truth that survives a gap, we archive raw data with uncertainties. Fund overlaps between missions and publish calibrations, not just products. That looks like flying a successor a year early to run shoulder to shoulder with the Elder, handing off a baseline cleanly. It looks like national libraries that mirror space weather and geomagnetic archives. So researchers 50 years from now can reprocess today's best with tomorrow's better. We should protect the small memories too. Community observatories that log field strength and aurora where the map is thin. Local outage reports stitched to magnetometer traces. So utilities learn from neighborhoods, not just nodes. Pilots' notes about HF fades and dose bumps tied back to the storm timeline. In noisy eras, dozens of little ledgers beat one grand one. A shared playbook holds it together. Utilities, airlines, satellite ops, and space weather centers sitting at the same table twice a year, running drills with the same maps, arguing over thresholds now instead of during a flare. After action notes that name what worked and what didn't, then get folded into procurement, training, and policy. The people in those rooms change. The playbook stays. Meaning isn't in a headline, it's in the choices that make a dent ordinary. An avionics engineer who argues for heavier shielding around a clock can. A program manager who eats mass to add a neutral blocker at a substation. A mission planner who chooses to lose 3 images a day to keep a detector alive for 3 extra years. No one writes monuments for that. We live off it. There's a quieter piece of the contract. Humility. The core will keep its secrets. The sun will keep its moods. Our job isn't to announce fortune teller dates. It's to publish uncertainty, verify forecasts, and admit misses. Trust grows in that soil. When a forecaster says, southward field inbound, these corridors, these hours, and the grid stays up, people believe the next map. And yes, leave room for joy. The aurora that slides over a city that rarely sees it is the same physics that makes a dispatcher bend a track. Walk outside, look up, then go back in and write the checklist better. Back up your backups and hydrate. Our maintenance is how we care for strangers. Our memory is how we keep promises to people not born yet. Our meaning is what we build when the engine light blinks, and we choose to tune the engine instead of curse the dash. The shield won't smooth out for us. We smooth out for each other. The countdown is boring. That's the point. A softer shield turns rare bad days into expensive ones, and ordinary days into checklists you follow without drama. If this story landed, it's because boring saves Thursdays. If you want the deep dive on how we forecast, harden, and drill, watch the next episode in this series. Subscribe, share this with the grid nerd or satellite friend in your life, and keep the light steady while the sky gets stranger.